A couple minutes late because people have run off to the bathroom. I'll let you know when we begin.
But normal. Yeah. Yeah, that's it doesn't follow. Okay, welcome back. For our second talk of the morning, we'll have Bao Zhigang tell us about phase transition of eigenvector for spiked random matrices. Please begin.
Okay, so first of all, good morning to those in the US and good evening to those in Asia, and also thank the organizers for the invitation. Today, my talk will be on random matrix only, so it does not involve free probability. But I think further development of this topic may involve free probability. And more specifically, my talk will be on the so-called spiked random matrix model. So for this random matrix model, we know there is a very famous phase transition called the Bbp phase transition due to Baker, Ben-Hus, and Piche, which states that the eigenvalue, the leading eigenvalue of the spiked random matrix undergoes certain phase transition, and when you change the strength of the spike. So today, what I'm going to introduce is a kind of the eigenvector analog. So I'm going to show that what is the limiting distribution of the eigenvectors associated with the leading eigenvalues in the subcritical, critical, and the supercritical regime of the Bbp transition. And we will mainly focus on the critical regime. So this is joint work with Wang. And in the first few slides, I will record some well-known results on this topic. And also, I'm going to use this first few slides to specify some notations and scalings in the conventions. And so first of all, let's record the definition of a model is Wigner matrix. And I think it's already well known. So this is just a random emission matrix. The entries are independent, but up to symmetry. And the mean of them are, the entries are 0. And we choose a scaling that the off-diagonal entry have 1/n variance. And for the special GUE, we choose the same scaling. So the variance are always 1/n, so that we know the eigenvalues were distributed on the interval from -2 to 2. And the global distribution of the spectrum is given by semicircle. And I will use the capital lambda to denote the eigenvalue of H, and the Vi is the unit eigenvector. And so for the fluctuation of the leading eigenvalues, and it is well known that for complex Wigner, the distribution is Tracy rhythm. And for eigenvectors, especially for GUE, we know that the eigenvector is distributed on the unit sphere. So if you project this Vi onto any given direction, it is given by complex Gaussian. So here I take a square because there is an ambiguity on the choice of the phase of the eigenvector. And so from this limiting law, we know that the scale of this projection square itself is 1/n. And now both of these two laws have been proved to be universal. So these results, we already know them to be true for generally distributed complex Wegener matrix. And then here comes our main model in this talk. It is the so-called spiked Wegener matrix. In addition to the Wegener matrix, we have K orthonormal unit vector, orthonormal vector, and also K positive numbers. They are all deterministic. And then we consider this spiked Wegener matrix. It is a sum of the Wegener matrix and a rank K deterministic matrix. So from the randometry point of view, very often we view this Wegener matrix as our major part because this is a resource of the randomness. And we view this rank K matrix as a certain perturbation. But in application, usually we think this rank K matrix is our major part. So very often it's a mean signal, say, and you can roughly think this Di as the strength of the signal, and you can think this Ui is something containing some structural information of the signal. So the signal part is what you want to know, but very often you get the polluted data. So here this H is understood as a noise. So the polluted data is this HDU. The primary goal for this model is you try to get some information of this true signal from this noise data. And a very simple idea is to use the leading eigenvalue and the corresponding eigenvector to estimate this Di and the Uis, because Di and the Ui are simply the eigenvalue and the eigenvector of this matrix. And so this motivates us to consider the extreme eigenvalues and eigenvector of this spiked Wegener matrix. And because the perturbation is fixed rank, so the global rule of the eigenvalue of this model is still given by a semicircle, but the limiting behavior of the leading eigenvalue and the corresponding eigenvector may be very different from the original Wegener matrix. So here is some well-known results about the leading eigenvalue and the eigenvector. So on the first order, actually the limiting behavior depends on the strength of the signal. So it depends on the size of the Di. Now, if this Di is not sufficiently large, it is bounded by 1, then still the leading eigenvalue will go to 2, and it will be the same as the original Wegener matrix. And you can also consider the projection of the eigenvector of the spike model onto the true signal direction. Now, in reality, we of course hope this projection to be close to 1. If this is true, then you can use this Wi to approximate or to estimate this true signal. But unfortunately, when the signal is not sufficiently strong, this projection is almost 0. So you can think that this Wi does not contain any useful information of the true signal. Now, once the signal is strong enough, once it goes beyond 1, and the lambda I will jump out the support of the semicircle and converge to some number strictly larger than 2. And the projection of Wi onto the true signal will also go to some non-zero number, although it's still not 1. But from this right-hand side, you can also see when Di is sufficiently large, when Di goes to infinity, this guy will go to 1. This, of course, fits our intuition, because if the strength of the signal is sufficiently large, you can use the eigenvector of the spike model to estimate the original signal. And so this is the first order behavior. If we move to the second order, asking for the fluctuation of the eigenvalue, then here comes the famous Bbp transition. And actually, the fluctuation of the eigenvalue will show up on a much finer scale. So it depends on whether Di minus 1 is at the scale of n to the minus 1/3 or below or above that. The Bbp transition depicts the phase transition of the fluctuation of the eigenvalue, but it was originally done for the spike covariance matrix. But since we are talking about spike Wegener, so I cite the work of Piche. And so very roughly speaking, when D1 is subcritical, and then the distribution is still given by Tracy rhythm, so it will be the same as the original Wegener matrix without spike. Now, if D1 is in the supercritical regime, then the distribution is given by Gaussian for spike GUE. And now if D1 is exactly on the critical regime, then the distribution is certain intermediate form. And here I omitted the detailed expression due to the time constraint, but you can certainly refer to this paper for the definition. And there are lots of work on after this story, and especially in the supercritical regime and the supercritical regime, the distribution of the leading eigenvalue has already been well understood for even for generally spiked Wiegand matrix. But actually for the critical regime, the understanding is still very much limited to the Gaussian and the Gaussian-like Gaussian-like matrix. As far as I know, this is probably the only work which has dealt with the critical regime but for generally distributed Wiegand. But still, they impose some very strong condition. So the universality of the critical distribution has not been fully investigated. And now if we move to the eigenvector, we can then ask what is the fluctuation of the eigenvector in these three regimes. And in the supercritical regime.
May I ask a question?
Yeah, sure.
Your previous slide.
Last slide. Okay.
Thank you. Are you envisioning D? The DIs also depend upon N?
Oh, you mean whether DI is independent of N or no? DI could be N dependent.
Okay.
Yeah.
So the region refers to the values of N, that how they.
Yes. Yes.
And when you say your arrow, is that converging when N goes to infinity? So I don't understand this.
Yeah. N go to infinity. Yes. Sure. N go to infinity.
Okay, but if N goes to infinity, and the DIs don't depend on N.
DI depend on N. DI may depend on N.
Does depend on N. Okay.
Yeah, may depend on N. Yes.
Okay, thank you.
Yeah. And then, so what we care is the counterparts for the eigenvector. And in the supercritical regime, this work shows that actually the projection, if I only consider the rank 1 case, say, and I care about W1 onto U1, the projection. And again, this guy is given by complex Gaussian, but this time the scaling is D-dependent. So especially if I choose this D1 minus 1, this guy, if I choose it to be exactly minus n to the minus 1/3 plus epsilon, then the scaling of scale of this guy will be n to the minus 1/3 minus 2 epsilon. So remember that if there is no spike, this projection square will be of order 1 over n, as we shown in the first few slides. So you can think that when there exists a supercritical spike, but the spike is very close to the critical regime, in this case, there is a weak bias of this W1 towards this U1. Although the bias is not order 1, it is still much larger than 1 over n. Now, actually, in this work, they also show that the same results hold for the projection of any Wi onto U1 for fixed I. So actually, if you replace this W1 onto U1 by Wi onto U1 for any fixed I, Wi means the eigenvector associated with the I's leading eigenvalue, then the result is almost the same, especially the scaling will be the same. So that means that if you have a spike which is close to the critical regime, then it will not only cause a bias for the corresponding eigenvector, it will cause a bias, a weak bias for all Wi's for any fixed I. Okay, so this is a phenomenon observed in this work. Now, if we go to the supercritical regime, and we know there is an order 1 bias of this W1 onto U1, as we have shown in the first order behavior, and then the fluctuation parts consist of 2 terms. Now, the first term is a Gaussian term, and the second term depends on the structure of the true signal and also the distribution of the Wiegand matrix. Now, imagine that if you have E1 here, so if U1 is E1, the standard basis, and the H is some non-Gaussian Wiegand matrix, then this guy will be the first entry, the 1-1 entry of H, and this will not be Gaussian anymore. So if you sum up these two, then this distribution may no longer be Gaussian. So indeed, this fluctuation in the supercritical regime will be dependent of this U1 and also H. So we call this as a non-universal result. And now, if you approach the critical regime from above, say if it's D1 minus 1 equal n to the minus 1/3 plus epsilon, which is indeed in the supercritical regime, and this also tells you the scale of this guy. So now from this two scale, you can naturally guess that if I'm exactly on the critical regime, then the projection squared should be exactly of order n to the minus 1/3. So the remaining question is, what is the limiting distribution in the critical regime? If di minus 1 is exactly n to the minus 1/3. And so now, as I said in the eigenvalue part, the understanding for the critical regime is very much limited to the Gaussian case, even for eigenvalue. So here for eigenvector, it is also very reasonable for us to start with the spiked GUE rather than general spike Wigner matrix. And so from now on, we're going to consider this special case where H is a GUE. And we would like to consider the general pair, IJ pair here. So we consider the projection of WI onto any UJ for any fixed I and J. This is because, as I said, when there is a spike close to the critical regime, it may cause bias for a lot of eigenvector, not just the corresponding eigenvector. So this motivates us to consider such a general pair, IJ pair. And now also because H is a GUE, by unitary invariance, we can consider this canonical model. So we choose UI to be EI. And then this quantity boiled down to be the J's component of the ith eigenvector of this model. And we can further simplify the notation to HD for the matrix and the WI for the eigenvector. And now our task boils down to the limiting distribution of such eigenvector components. And now, in order to study the limiting behavior of an eigenvector component, we will start from this, the so-called eigenvector eigenvalue identity. There is a very nice recent survey which introduced the history of this identity. And now, so if you want to consider the J's component of ith eigenvector, you can express it in terms of the eigenvalue of the original matrix and the eigenvalue of its minor. So which minor you need to consider depends on which component you want to investigate. So if you want to consider the J's component, you need to consider the minor with the J's column and the J's row deleted from this original matrix. And now, so the expression consists of two products. This is the ratio between two products. And in each term, in the product, you see this common term lambda I of A. And so lambda I of A plays a special role in this formula. This is of course easy to understand because you are considering the ith eigenvector. So the corresponding eigenvalue should play a special role in this expression. So this is some formula very easy to remember actually. Now, if you want to consider the limiting behavior of that guy with such an expression, apparently you should have some understanding on the relation between the eigenvalue of the original matrix and its minor. Then the first thing pop out is of course the Cauchy interlacing. We know that for an emission matrix, the eigenvalue of the original matrix and its principal minor are interlacing. So specifically for our model, now if we consider the spiked GUE, and in order to ease the presentation, let me further restrict to the case when k equal 1. Although our work dealt with general case, but here let's consider the case when there's only rank 1 spike. And our D is in the critical regime. Here, this D is some constant. And further, I consider the projection of Wi onto E1 because E1 is the direction of the spike and for any fixed I. And now according to my Eigenvex eigenvalue identity, I needed to consider the eigenvalue of this matrix, original matrix, and its minor with the first row and the first column deleted. So now for simplicity, I denote the eigenvalue of HD and the eigenvalue of the minor by lambda I and the mu I respectively. And then my formula tells me that I can write this guy in terms of this ratio. And I can further also write it in to two factors. So depending on L smaller than I or larger than equal to I. And now if we want to have a closer study on the limiting behavior of that guy, apparently Cauchy interlacing is not enough because this is not quantitative. Right? So we will need some quantitative version of Cauchy interlacing. I call it quantitative interlacing. Now, so I want to see how this lambda particle and the mu particle interlace. And so let me first condition on this minor matrix, okay? So the strategy is to condition on that part, and then we start to change this D. Let it vary from the subcritical to critical and the supercritical, and then we see how lambda change. So here in this picture, I fix this minor matrix. So the mu particles, they are fixed, and then we start to change this D. Now, here I do not consider the full subcritical and the supercritical regime. I consider the case when D is far away from 1, okay, by order 1 distance, in order to make the pictures more visualizable. So now, if I'm in such a subcritical regime, actually, although we know by Cauchy interlacing, lambda 2 is between mu2 and mu1, actually lambda 2 favor mu2 more than mu1. So actually this guy is closer to mu2, and there's the order of the distance is 1 over n. So here this 1 over n is not exact distance, it means the order of the distance. And now when this D move to the critical value, this lambda 2 will move rightwards, and eventually it will be in sort of the middle between mu2 and the mu1. So you can say typically lambda 2 will sit neutrally between mu2 and mu1 in the critical regime. Now, if I further move to the supercritical regime, the lambda 2 will move toward to mu1. So eventually it will be of distance 1 over n to mu1. And this time, this lambda 1, the largest lambda particle, will jump out the support of the semicircle, and it has order 1 distance from all the other particles. And now, so this is a picture for what happens when you condition on the minor matrix, and you start to increase this D from the subcritical to supercritical. And actually the fact that the distance between mu1 and lambda 1 is much smaller than the distance between lambda 1 and lambda 2 in the subcritical case, and also the fact that lambda 1 is far away from all the other particles, they are sort of the key inputs for the derivation of the eigenvector distribution in these two regimes. And actually in both of these two regimes, there exists some perturbative argument based on the green function. And so as I said, the quantitative interlacing are the key inputs for these two perturbative arguments. Now, these two perturbative arguments in these two regimes, they are different, but when you start to approach the critical regime, both of them will fail. And it's essentially due to the fact in the critical regime, this distance between these lambda particles and mu particles at the edge, they are all of the same order n to the minus 2/3. So due to time constraints, I'm not able to introduce the detail of these perturbative arguments, and I'm not able to explain why they will fail in the critical regime. But I want to emphasize that this picture is the essential reason why the perturbative argument does not work. All right, now if we cannot use any perturbative argument, we can still use this expression. So we go back to the eigenvector, eigenvalue, identity, and now from the quantitative interlacing, we know that when L is fixed, and because I is also fixed, then when L is fixed for small L term, the distance here, the difference here and here, they are all of the same order, n to the minus 2/3. And the fluctuation of these differences are exactly on this scale. So you can imagine that when n goes to infinity, the randomness of these ratios, they will survive. So you really needed to know the joint distribution of the lambda particle and the mu particle when the index are fixed, okay? So now, but for this part, I can further separate it into two parts. The first part is for relatively small indices, and the second part is for relatively large indices, say. Now, here I can choose this K to be sufficiently large. When K is sufficiently large, you can imagine that this mu L2 and the lambda L2, they will move far away from this lambda I. So this I is fixed, okay? Now, in this case, the fluctuation of this lambda I and the mu and the lambda L, they may not affect this ratio too much because as we know, the fluctuation of the lambda I, according to the Tracy-Wiedemann law, is actually on the scale n to the minus 2/3. And when the particle move to the bulk, the fluctuation is even smaller. But when the difference become larger, the fluctuation of the individual term may not affect this ratio too much. So you can imagine that when this index become large, this part is sort of the robust part. So you can imagine maybe some sort of some perturbative argument may work to derive the limit of this part, okay? And this is indeed the heuristic behind the limiting distribution of that guy. The randomness of this guy essentially comes from the small L term. So when L is relatively small, you really need to derive the joint distribution of the lambda and the mu particles. But when L become large, this part you can estimate them directly in a robust part, and this part will not contribute to the randomness, and it will contribute collectively a deterministic factor to the product. So this is a picture behind all the detailed analysis. And now, because with this heuristic, of course, what we need to know is first to derive the joint distribution of the edge particles. So we first needed to write up the joint distribution of the lambda particles and the mu particles. And fortunately, this is actually already in the literature. And these two systems of particles are interlacing, and together they form a determinant point process. And this DPP is a so-called GUE minor process with external source. And if you do not have the spike, we will call the joint distribution of the original matrix and its minor, the eigenvalue of the original matrix and its minor as a GUE minor process. But if you have a spike, we say this is a GUE minor process with external source. And so this is a determinantal point process. And then you try to investigate the edge scaling limit or bulk scaling limit. And especially here, what we need is edge scaling limit. So we want to find the joint distribution of the lambda particle and the mu particle when the indices are small, they're fixed. So then the edge scaling limit of this DPP is given by another DPP. It's a so-called extended Array process. And again, this is two systems of particles, they are interlacing. And this Ci serve as the limit of the lambda i's, and this delta I serve as the limit of the mu i's. So they still inherit their interlacing property. And then again, they form a determinantal point process. And this is the kernel for the determinantal point process. And then we can prove that for any fixed K, the edge particle, if you subtract 2 from them and multiply by n to the 2/3, and they will converge to the Ci particle and the delta particle jointly, right? And now, if you take logarithm of the Eigenvalue component squared, originally this guy is a product. If you take log, this becomes a summation. And this sum, you can separate it into 3 parts. The first part is the edge part. As I said, we expect this part to contribute essentially to the randomness of this guy. And the remaining 2 parts, and if you put them together, it's also fine, but for technical reason, we prefer to separate them. And these 2 together, they will actually not contribute essentially to the randomness when I choose K to be sufficiently large. And now, according to this lemma, I can immediately get this consequence. The right edge parts will go to this guy when K is fixed. But here, I further put log K divided by 3 here, because later I'm going to send the K to infinity as well. And this guy will counterbalance the leading term of this part. Without this term, this guy will simply go to infinity, right? So now for these 2 parts, I can estimate them by some robust method. Although the estimate is also very complicated, but eventually what you can get is both of these two things, they will not essentially contribute to the randomness of the eigenvector. But here you get an error in k, so eventually you need to send the k to infinity as well. So here what we are going to do is we sum up these three parts, and these two guys, they just cancel each other, and eventually we need to first send n to infinity and then send the k to infinity, and finally we get such a representation of the limiting distribution. So this guy itself is a large k limit of this right edge limit. And now this limit, we denote it by CID infinity. Now, but then somebody may be not so happy with such a representation of the limiting distribution, because in some sense, this is still very complicated, right? And also we need a key thing to justify, a key thing needs to be justified is whether this limit is well defined or not. So whether this guy itself is indeed a random variable or not. Now, so this is the first thing we need to justify. We need to prove that this limit indeed exists almost surely. And now, besides of that, actually we didn't, so far we haven't got too many other properties of this limiting distribution. But at least once you show this guy exists almost surely, you can claim that under this scaling, indeed the eigenvector component converge weakly to some random variable, okay? Although we do not know too much about the property of this random variable. And also because this guy is given by the extended array process, which has an explicit kernel. So hopefully you can take a step further to investigate some property of this guy. So for instance, maybe you can investigate the tail property of the distribution of this guy, but so far we haven't got such results. Now, here is a summary on what we have got. And again, for simplicity, I only stated the results for the rank 1 case. Now, as I said, first of all, we need to show that this limit indeed exists almost surely. And then we can prove that this guy will converge in distribution to this limiting random variable. And because we consider the rank 1 spike and we choose the spike direction to be E1, then all the other directions are not the direction, are a non-spike direction. So if I consider the projection of Wi onto other direction, then they will still be Gaussian. They will still be the same as the case when there is no spike. And now, as I said, the next step is try to prove some property of this guy, for instance, like the tail property. But so far, what we have got is very limited. The only thing we have proved in our current work is we can show this guy indeed does not degenerate. So it is not a constant. It is indeed a random variable. Okay, so this is the only property we know about this limiting distribution so far. So I think due to time constraints, I will just omit all the technical issues and stop here. Thank you for your attention.
Yeah, so Zhigang, so why did you choose the n to the power 1 or 10? I mean, so in the Bao case, is that just for technical convenience?
Sorry, please say again.
So there's, I mean, so go about one side 15, I think.
Here, 15.
Yeah, so there's a term 1 n to the power 1 or 10. So is there any reason you choose
this is purely technical. This is purely technical. Yeah, you can also separate the intermediate regime and the bulk regime at some other index. It's also fine.
Okay, so and is the question more difficult if you have two identical critical spikes?
Identical critical spikes.
Yeah, because here you only start with 1, right? For if I have one spike, but its multiplicity is 2.
Okay, so you mean you want to estimate the spike in the critical regime or in the subcritical regime?
No estimation. I only want to know what if you have the two spikes, but they are the same.
You mean two spikes, they're the same. You mean multiple spikes?
Yes.
we can also consider this case. So we do not assume these DIs to be distinct from each other. So they can be completely the same. It's completely fine.
Okay.
Yeah.
Thank you.
Okay,
Yeah, so say you only cared about the quantitative interlacing statement. Are you able to prove that for general complex Wigner matrices?
So as I said, even on the eigenvalue level, the universality has not been fully proved. And the only work is by Ferro and the Pische. I think they make some very strong assumption, like the distribution of the entry should be symmetric and something like that. And using moment method, you can prove the universality of eigenvalue. And we believe the eigenvalue distribution should be also universal in some high level. Now, whether a distribution is universal or not can be heuristically judged from the following facts. You can simply think whether the limiting distribution depends on locally on the particles. So as I said, essentially the randomness of this guy depends only locally on the edge region, right? And the remaining particles, they only contribute collectively a deterministic factor. So in some sense, this guy is also a local statistic. The randomness is also a local statistic in some sense, although it depends on all the particles. So because of that, we believe that this distribution should be universal in some sense. But how to prove it is still not so clear. Now, if you make some very strong assumption, like the enough moment matching, I think the current technique will be enough. But if you do not have any moment matching, then maybe you need to develop some dynamical method, like the dynamic method of Edishi-Yao school. And then this will involve the dynamic approach for the minor process. And then this will be very, very unclear for me how to do it. And so if you have a Dyson-Brownian motion for the original matrix and also have a Dyson-Brownian motion for the minor, these two Dyson-Brownian motions, they will be strongly coupled. So this is a technical difficulty on pursuing this dynamical approach for this problem. But if you have enough moment matching, I think you can prove it without too much difficulty.
Thanks.
any further questions? Yes.
Have you thought about the GOE or other real models where the
Yeah, the GOE is a nature problem to think, but then this is not a deterministic, the determinantal point process. So the joint distribution of the minor process, I think it's not available in the literature for the real case. But maybe you can think about some other methods. So maybe you can think some method of Varag on this array operator stuff. So I'm not sure whether this will work, but this is an alternative way to think. So we haven't tried that yet. But maybe you can also follow the current way to derive the joint distribution of the minor process. But you can expect it to be much more complicated, I think.
Thank you.
Any further questions? If not, let's thank Zhigang again.
Okay, thank you.
So we'll take a short break and resume at